Can you hear me?
Yes.
Okay. I would like to say first is thank you to organizing committee to organize that great event. Then I would like to introduce my mentee Serdar Çite, and I would like to say also thank you uh, for his hard work, and I would like to express that in this process I have learned much from him, as well as we studied Poincaré group representation. We choose that representation to actually as an introduction to quantum field theory. I believe this process will help him for his further study. And lastly, I'd like to say thank you for to all attending, and I wish you have a great talk.
Hello everyone, I am Serdar. First of all, I want to thank PRP Turkey organizers for this amazing event. And I want to thank my mentor Faruk for his guidance. And thanks to all participants. My topic is the Poincaré group representation, which is just the symmetries of the special relativity. And I will apply that to quantum mechanics. And I will make this through the unitary representation of the Poincaré group. Here's my outline. I will first talk about the structure of the Poincaré group. Then I will talk about the unitary representation of the symmetry group. And I will briefly mention the Lorentz transformations. And I will examine the Lie algebra of the Poincaré group, which is the Poincaré algebra. Now let me make some definitions first. The Lie group G is a differentiable manifold such that its group operations, which is the multiplication of two elements and taking the inverse of an element, are differentiable. And the algebra is just tangent space at the identity. Now, Lie algebra has some additional properties, the most important one being the Lie bracket. The Lie bracket is a bilinear map satisfying these two conditions. Lie bracket of any element in itself is equal to 0, and the second condition is called the Jacobi identity. Now, the Poincaré group is the group of all isometries of the Minkowski spacetime. Minkowski spacetime is just a four-dimensional space with time as its four-coordinate. It has a special metric called the Minkowski metric, which is just a 4x4 diagonal matrix with the entries -1 for the time coordinate and the 1s for the space coordinate. Now, any isometric group may be represented as translations product with isometric space in the origin. Now, I want to show you an intuitive way to see that Poincaré group is a Lie group. Now, assume these two spaces are differentiable manifolds. Now, there is a theorem in differential geometry which says that any product of two differentiable manifolds is still a differentiable manifold. So, Poincaré group is a differentiable manifold. Its operations are matrix multiplication and translations, which are differentiable. Thus, Poincaré group is a Lie group. But I will talk about these operations more in detail later. Now, let me give you some basic quantum mechanics. In quantum mechanics, imagine a physical system. The physical system is represented by vectors in the physical Hilbert space. The Hilbert space is just an infinite-dimensional complex vector space and has a nice property called the inner product. Now, I assume a complete orthonormal basis for the physical Hilbert space. The probability of measuring if a system is represented by the state psi n is given by this inner product squared. Now, notice that if two eigenvectors are separated by a constant with magnitude 1, then this probability relation is the same for these two eigenvectors. So I call them they are in the same range and they have the same physical consequence. So array is just an equivalence relation between such two eigenvectors. Now, of course, the probability of measuring a system in a range Rn is just the same as the eigenvector probability relation. Now, in physics, we measure physical quantities like energy and momentum, and there is a theorem which says that these physical quantities called observables must be represented by linear Hermitian operators on the physical Hilbert space, which is just A dagger equals A, and the dagger is just conjugate transpose. Now, when I talk about the symmetric transformation, I talk about the transformation between two rays, which satisfy this probability relation. So Wigner's theorem says that for any symmetric transformation between two rays, this transformation must be represented by an unitary, either unitary and linear operator or anti-unitary and anti-linear operator on the Hilbert space. Now, unitary operator is just this definition, which preserves the inner product, and U dagger equals to U inverse. Now, proof of this Wigner's theorem is actually quite long, but I will give you the main idea. So I can assume a complete orthonormal set of state vectors. They satisfy this probability relation. So I choose a candidate vector, gamma k, and transform the gamma k may be expanded by this orthonormal basis. Now, let U be the operator of this transformation, and but it will satisfy these probability relations. So the coefficients of this gamma and transformed gamma should satisfy these two conditions, which says that real part of the coefficients stay the same, but imaginary parts may be either positive or negative. So we have actually two choices here for the operator U. It may choose plus option or minus option. So let's choose the plus option. I let U act on two arbitrary eigenvectors, and I see that this U actually preserves the inner product, so it must be unitary. And linearity follows. The other choice, the minus choice, actually leads to anti-unitarity and anti-linearity, which is the complex conjugation here. Now, in physics, symmetric transformations actually form a Lie group structure, but the ordinary representations in general doesn't follow the group multiplication law. So let's consider these two transformations between rays. Now, notice that this UT2, UT1 and UT2, T1 is actually in the same ray. But since they're in the same ray, they may be separated by a phase with magnitude 1. So in general, the group multiplication law is not respected. But if the phase is equal to 0, then there is no problem. So, and we call this an ordinary representation. But if there is a phase, we call this a projective representation. Actually, the subject of projective representation is actually quite broad subject. But for now, I just assume that the phase is equal to 0. Now, I want to consider the Lie algebra of the symmetry group. So let me take the elements near the identity. Since identity is unitary, the elements near the identity should be unitary as well. I make the following expansion for epsilon being a real infinitesimal and the operators. I apply the unitarity condition here, and I see that T must be Hermitian. And actually, since T is Hermitian, T is a possible observable in physics. To be more rigorous, this expansion is just a differentiable, but on the differentiable manifold structure, with when it crosses the identity when epsilon equals to 0. And since I'm an infinitesimal neighbor of the identity, I may write a continuous function between elements of the symmetry group. There is a function f such that it respects this group multiplication law. And since the product of any element with the identity equal to itself, this function should satisfy this property. And I take the coordinates of the identity as 0. And this theta is just a set of continuous parameters. Now, with respect to theta, I make the following expansions on function f and my unitary operator u. And notice that it's just a Taylor expansion. And I apply these expansions on the group multiplication law, and I get most of the terms just match automatically, but I get the following equation. But this equation alone doesn't tell us much. So I apply the equality of second derivatives to my unitary expansion, and I see that T must be symmetric. I apply this symmetry condition onto this equation, and I get the following commutation relations. Now, this commutator is actually a Lie bracket. The commutator of any operator with itself is equal to 0, and it's linear in each entry, and it satisfies the Jacobi identity. Now, I claim that this is the Lie algebra of the symmetry group. First of all, the space of linear Hermitian operators is a vector space. And when I remember the differentiable part gamma I defined, its derivative at the identity should be equal to tangent space at the identity. And I think that it is spanned by IT. And so this is the Lie algebra of my symmetric group. And I collect these two constants into a single constant, and it's actually called the structure constant of the Lie algebra. Now, I will briefly talk about the Lorentz transformations. Transformation between two set of coordinates in the Minkowski spacetime. I let my x0 be the time coordinate and others be the space coordinates, and I set the speed of light equal to 1. Now, any transformation between two set of coordinates should respect this transformation law, and it's actually just a transformation of metric tensor under a change of basis. Then our metric tensor eta is just a Minkowski metric, and any x prime satisfying this transformation law should be linear in x. So I plug this x prime into equation above, and I see that the matrices lambda respects this equation. The matrix lambda is just a constant matrix, and I is just a constant vector. So I want to show you that this Lorentz transformation actually has a group structure. So I take the determinant of this equation, and I see that determinant lambda is either 1 or -1. So lambda inverse exists. And I may get the inverse transformation of any Lorentz transformation into the following equation. Now I apply the two Lorentz transformation L1 and L2 consecutively, and I see that their combination is also a Lorentz transformation here. These summations are just the Einstein summation convention, which there are hidden sums over here. If, for example, this nu appears both on the upper side and the lower side, so I just sum over this variable mu. Now, the ident transformation is also Lorentz transformation, is trivial. And we see that Lorentz transformations follow this group multiplication law. Now, the whole group of Lorentz transformation is called the Poincaré group, or the inhomogeneous Lorentz group. And it has several subgroups. Let's consider the transformations without translations. They form a subgroup, and it's the O1-3 part I mentioned at the beginning. Now, another special subgroup is just the determinant lambda equals to 1 and 0,0 component lambda is bigger than or equal to 1. This subgroup is called the proper orthogonal Lorentz group. And this is actually the part of the Poincaré group which is connected to identity. This is where I make the expansion on my Lie algebra slides. Now, since Poincaré group is a Lie group, there exists the induced unitary representation of this Poincaré group on the physical Hilbert space. And since I assume it was ordinary, it just respects the group multiplication law as well. Now, identity transformation is demonstrated here. I follow the same steps as I did before. I consider an infinitesimal expansion around the identity, and I see that it is given here. And it follows the transformation law that lambda followed before here. Now, with the help of in this lowering and raising operators, I see that this infinitesimal omega should be an antisymmetric tensor. Now, I again expand my unitary operators around an infinitesimal neighborhood of the identity between infinitesimals omega and epsilon. I get the following expansion. Now again, I want this to be unitary since it's around the neighborhood of the identity. And I apply the unitary condition, and I see that these operators J and P must be Hermitian as well. So they will be observables in our physical systems. And since the coefficients of omega are antisymmetric, the corresponding operators J must be antisymmetric as well. Now, I want to find out how my operators J and P behave under Lorentz transformations. So I choose an arbitrary Lorentz transformation U lambda B, and act it on my unitary expansion by conjugation, demonstrated here. It's actually quite long calculation. I make the following calculation with the help of inverse matrix definition shown here. And after that expansion, I equate the coefficients of infinitesimals on both sides of the equation, and I get the following transformation laws for J and P. Now, you see that these operators P are actually invariant under translations, but J is not. But I can make this go further. I can choose my lambda and B infinitesimals as well. with infinitesimal zeta and kappa. So the conjugation above can be expanded. And when I expand this arbitrary Lorentz transformation as well, I get the following relation, just a long calculation. Now, this doesn't tell us much. So I know that this commutator is a Lie bracket. So let me use the bilinearity of the Lie bracket. And I put these relations into this final form. And with the same arguments as in the previous slides, I claim that this is the Lie algebra of the Poincaré group. Now, notice that this P actually form a abelian subalgebra of the Lie algebra. And this operator J does not commute with either itself or the operator P. Now, operator P0 is actually special in physics. It is called the Hamiltonian operator, and it represents energy of a physical system. Now, there is a theorem in quantum mechanics which says that if an operator commutes with the Hamiltonian, then it is conserved. So, when we look at these operators, we see that these following operators commute with P0. These are the momentum 3 vector and angular momentum 3 vector. So we get the following conservation of momentum and conservation of angular momentum. There are remaining operators. These are not conserved. It's actually the Lorentz-Booth part of the Lorentz transformation. And we do not actually use them in the physics because they are not conserved. So they are of less importance. Now I want to finish my talk by giving two examples of my unitary representation. There exists a map between Lie algebra and the Lie group, which is called the exponential map from the Lie algebra to the Lie group. But for abelian subalgebras of my Lie algebra, this exponential map is directly applicable. So consider pure translations. They of course form an abelian subalgebra, and their corresponding generators are the P part of my expansion. So when I take the exponential map, I directly go to the unitary representation of these translations, and I see that they are represented by this unitary operator. Similarly, the pure translations also form a abelian subalgebra, and their corresponding operators are the angular momentum 3 vector. And when I apply the exponential map, I get the unitary representation here. So here are my references: Stephen Weinberg, quantum theory of field,